So let's say you have some code and you want to know who the author is. So you might compare the coding style of the code you have against a set of code where you do know the author. And you say that the unknown code is written by the person whose coding style most matches it. And that's source code attribution. Previous research has achieved high accuracy on this kind of problem. In 2015, Calscom Ismail published a classifier that achieved much higher accuracy over larger groups of authors than anything before, 98% over 250 programmers. And for their dataset, they use Google Code Jam, which is an annual programming competition that's also used by PriorWorks. And we use this as well. So there's this powerful source code classifier. My question is, what if you don't want your code to be attributed to you? For example, what if you're developing a popular cryptocurrency and you don't want people to know who you are? And more generally, you might develop software outside your day job that you don't really want to be connected back to you for privacy reasons. So you might want to write your code that tricks a source code classifier. Or what if you're a developer in a country with censorship? Someone making an anti-censorship tool might want to preserve their privacy by writing code that doesn't look like they wrote it, by substantially changing their programming style, among other defenses. And on the flip side, someone might want to intentionally frame you by writing code that looks like you wrote it, creating a forgery of your style. So the main question here is it possible to fool source code attribution classifiers? And the answer, of course, is yes, we can. And it's important to note that we can ask this question because strong attribution classifiers like Calscom Islam's now exist. This is a nuke attack, so the classifier wasn't built with this in mind, and defending against this kind of attack was not part of their original design goal. So in order to learn about how we might fool an attribution classifier and why it might be possible, we ran a lab study in which we asked a number of programmers to try to modify code to imitate a certain author. So now I'll define source code attribution a little bit more formally so that I can talk about what it looks like to evade source code attribution. So back to this simple diagram of source code attribution. I've told you about the state-of-the-art classifier, so let's put a classifier into the diagram. The classifier is a black box that the code goes into, and out of all the possible authors, the classifier picks an author, in this case, author C. I'm going to use P sub C to represent some program or code written by author C, which goes into the classifier. And instead of showing the set of possible authors as a pile of stick figures, I'll use this notation at the bottom to show the authors that the classifier is trained on. Let's say it's 5 authors called A through E. So this is what source code attribution looks like. You take some code, for example, by author C, you put it into a classifier that's trained on some set of authors, which includes C, and the classifier outputs the name of the author whose style best fits the input code. And in this case, it's correct. So now that we've defined what normal attribution looks like, we can get back to the main question about fooling these classifiers. So what would you do if you wanted to trick the classifier? I'm going to call the person doing the tricking the adversary because they're acting adversarially to the classifier, not because they're necessarily malicious. The first thing that the adversary would do is look at code from the author that they don't want the classifier to recognize, and learn as much as they can about how that person programs. This is the original author of the code. In some cases, this might mean looking over their own code to learn about their own stylistic choices. This isn't what we tested, but it's a reasonable situation if you're trying to modify your own style for privacy. And if, like the participants in our study, you might also look at code from a target author if you're trying to make the classifier guess that some code is written by someone specific. So then they'll take some code and modify it to imitate the target author's style. And I'm going to call this forgery because the adversary is forging the target author's style. And there's another possibility. What happens if the adversary succeeds in changing the classification away from the original author, but the classifier attributes it to some third party other than the original author and the target author? For the purposes of this research, this is a semi-successful forgery because they hid the real author's identity, but they weren't able to actually create a forgery of the target author. And I'm going to call this masking because the adversary is masking the original author's identity. There are reasons that someone might want to actually intentionally create a mask, meaning that they don't have a target author in mind. But in this research, we focused on forgeries. So this is where the adversary fits in. You start out with P sub C, again, just some code by C. And then some adversary comes along and they manipulate the code and they create P sub C prime. They put it into the same classifier and the classifier makes a guess. And with forgery, the adversary's goal is to imitate a specific author. So here, if their goal was to imitate author A, then they would be correct and the forgery would have succeeded. And I want to emphasize again that the classifier is a black box for a reason here. We're not assuming that the adversary or any of the authors know anything about how the classifier works. If the adversary did know how it worked, they could tailor their attack to the specific classifier. So now I'll talk a little bit more about what we actually asked our participants to do. So broadly, in our study, we asked C programmers to act as the adversary and create forgeries. All the code in our dataset came from prior years of Google Code Jam, which is the same programming competition that prior work has used. We used C code from Google Code Jam, and unlike prior work, we linted the code to remove a lot of the typographical differences. We did this because we wanted to force the people making forgeries, our participants, to focus on less trivial differences than, for example, bracket placement. And in the real world, production code might not have these differences if a company has really strict style guidelines. So there are about 4,000 authors total with C files, with about 2 files each on average. We took the code from the five authors with the most files, who I'm going to call A through E, and we used these authors as input to our classifiers, and also as the original and target authors for the forgeries. And we used these authors, the ones with the most code, because we wanted to give the classifier as much data as possible to improve classifier accuracy. And we tested participants' forgeries against 3 versions of the state-of-the-art classifier, the one by Kaliskin Islam et al. The versions differed by the number of authors in their training set. And the first version was C5, trained on 5 authors, A through E, who are the authors with the most code. And this classifier has 100% accuracy. The next classifier is C20, trained again on A through E plus 15 random authors from Google Code Gem, and the precision and recall were in the high 80s. And finally, the last classifier is C50, trained on A through E plus 45 random authors, and precision and recall in the mid to low 80s. So we took our 28 participants and we asked them to act like the adversaries. First, we gave them sample code from 2 authors from the set of A through E, who I'm going to call X and Y, and then they modified code by one of the authors, let's say X, to look like the other author wrote it. And finally, we actually let them test their forgeries against oracles to see if they were able to fool the classifiers. We didn't tell them about the oracles until they had a forgery attempt in hand, so they didn't create their first attempt with the oracle in mind. And the only information they gained was what the classification decision was. They didn't know anything about how the classifier worked or why their forgery succeeded or failed. This isn't necessarily something that would exist for all adversaries, but in designing our study, we thought this might motivate our participants to continue trying to fool the classifiers. And in practice, we think that real adversaries would be much more motivated than our participants. And a real adversary could also very easily use the same classifier that we did, since it's open source, and depending on their original and target authors, they might also have access to code to train on. So in this example, this forgery px prime is fooling C20 and C50, since those classifiers are outputting Y instead of X, and it's not fooling C5. So in this example, the participant would see this, and they would continue to change px prime, or they'd choose to end the study. So now into the results. I'm going to first talk about a conservative estimate of adversarial success, and this is conservative because our participants were not experts in forgery creation. So this table shows how often participants were able to trick the actual classifiers. The columns are the classifiers, from left to right, C5, C20, and C50. And these numbers are from the final attempts the participants made, that is, after they had access to the Oracle classifiers. The first forgery attempts are slightly lower, but they're similar. The rows are the types of attack, forgery or masking. Remember that the participant's goal was forgery of a specific author, but even though we asked them to make forgeries, sometimes the classifiers output answers that were not the target author and also not the original author. And for the purposes of this chart, the masks include all forgeries as well. So the 66% here means that 66% of forgeries were successful against C5. 66% of the forgeries fooled the classifier into thinking the target author was the author instead of the actual original author. And down here, for C50, 86% of the forgeries resulted in some misclassification, meaning that they at least matched the original author's identity. So on non-adversarial data, remember, C50 had accuracy in the mid-80s. So this is a huge drop in accuracy on adversarial data to about 13%. And the lesson here, broadly, is that non-experts can successfully attack a state-of-the-art classifier. And this suggests that other classifiers might be vulnerable to the same type of attack. Okay, so we've shown that forgery is definitely possible, even when the adversary is not an expert and when the classifier performs really well on non-adversarial data. Now we're going to look at how these forgeries were created so we can start to talk about how to make a classifier that's more difficult to fool. One overarching lesson, before we even look at the modifications, is that forgers didn't know how the classifier worked or what it was looking for. So they weren't crafting forgeries specifically to fool that classifier. This means that forgeries in the wild might contain the same types of modifications. So moving on to the modifications, it's easier to actually just show an example. Here are 2 snippets of code, both by author C. They haven't been modified by anyone, they're just straight up author C. And they're also not functionally equivalent, so don't try to compare the functionality. And I've removed a little bit of the setup code. So as you look at these, try to think about what might be indicative of this author's programming style, or what you'd expect to see in other programs by this author. This is exactly what we asked our participants to do, except they had more code and a lot more time. So I'm going to highlight a couple things that people noticed. You may notice other things in there. At the very top in yellow, there's these funky pound defines. They use rep for a for loop. They just pound define it as something called rep. In the green, they have some variable names that are always the same. I, J, K, L, M, N, and then size and count. And then also some as well that aren't. When they read in data, they use scanf and nothing else. And then for loops, they typically use the rep that they pound defined at the top. But for their main loop in their main function, it's always while size minus minus. So these are a couple of things that participants noticed. And these are the same things that I just talked about, the stylistic elements, split into two groups. On the left, there's information structure, which just means variable names, syntactic decisions, macros like the reps and API calls, and control flow, which here just means loop type. So now I'll show you how people used these and a couple other modifications to create forgeries. I'll come back to this chart in particular and add a couple more after an example. So here's an example. On the left, I have some code by author A, which is not a forgery. This is just by author A, and all the classifiers correctly identify it as author A. I'm going to show you how someone created a forgery that maintains the functionality of author A's original code. So I just put the same code on the right. This is the code that will transform into a forgery. Right now, it's exactly the same. The code on the left will remain the original code, and the code on the right will transform into a forgery of author C. So first, we'll just copy in the distinctive pound defines. Then we'll change some variable names, CC and CA to size and count, and also change them down there so the code still works. Then change the input from CIN. We saw that author C liked scanf, so we'll change all the CINs to scanf. And then also thinking about loop type, we saw that they liked to use rep and size minus minus, so we changed those in the same way. And then the forger also moved that scanf up a little bit because we linted imperfectly. The linter didn't realize that rep was a for loop. So that's an example of a typographic difference. So this was a successful forgery. It fooled all the classifiers. And it's really interesting because the forger didn't need to understand the code to make these modifications. They could just make modifications, which means that they could make modifications to complex code that they don't understand. So here's the same chart that I showed you before. We did discuss a third group of modifications, typographic, which occurred because the linting wasn't perfect, like we saw. But for the sake of time, I'm not going to really talk about these because they're generally pretty easily to make with a linter, and not all authors will even have typographic differences. So here are a couple more modifications, including libraries that are imported, location where variable are declared, if statements, control flow keywords, loop logic. And all of these modifications, like the ones we saw in the forgeries, you only have to have a really local understanding of the code to make these. So I'm going to call them local changes. If you have a more comprehensive understanding of the code or the engineering decisions that went into it, you can make more complex changes, which we're calling algorithmic modifications. To make these, you need to know more about what the code is accomplishing and why the programmer made these. So information structure algorithmic modifications would be, for example, changing variable types or data structures or anything that intentionally affects memory usage. And it turns out that even though local infrastructure changes were really common, especially variable names and adding in libraries, no one actually made the more complicated changes, even though they came up in notes as differences they noticed between authors. We did actually see some algorithmic code flow modifications, like refactoring functions or inlining API calls, or making big changes to if statement logic. But for both categories, local changes were still a lot more common. There were lots of changes to loop type, like we saw, as well as loop logic, like making the counter increment instead of decrement. People found clever ways to add or remove control flow keywords, like go to, break, and assert, without really changing much of the surrounding logic. So there are two main takeaways from our analysis of the modification that created these really successful forgeries. One takeaway is that local modifications are very common, and the forger only has to understand a little bit about what's going on in the code. And another takeaway is that people often copied code directly from the target author's training set. In these forgeries, they were just copying single lines like we saw with the reps, but in the pilots, we saw some people copy entire functions and just use them as dead code. So it might be useful for a future classifier to look at code reachability and whether all the variables are actually used and analyze those sections of code differently. So in summary, we conducted a lab study with C programmers who produced forgeries, and we tested these against the state-of-the-art source code classifier. And the high-level summary is that our relatively unsophisticated adversaries were able to fool a state-of-the-art classifier, and the forgeries were successful, even though the forgers only made changes that didn't require them to really understand what the code was doing. Thank you, and I'd be happy to do it.
Questions? All right, 3 questions. 4, wow.
Okay. So can I start?
Okay, go ahead.
Okay. So one question I have, if you want to automatize all of this,
Sorry, I can't really
if you want to automatize, so not use any human, but to do it on a large scale.
To automate the modifications?
Yeah.
I think that's definitely possible. I think it's outside of my technical ability, but I think it would be really interesting. And I think there are also more difficult modifications that would be harder. Like changing variable names, you could very easily automate that. But changing other things would require a deeper understanding of the code. Does that answer your question?
Yeah, and my second question was, if a human would look at the code, you think it might be able to detect the forgery?
I'm sorry, I really can't hear you.
So if a human would look at the modified code, you think he could detect the forgery even if the classifier could not? So if you have an expert programmer which is looking at the modifications that the people have done, do you think he might be able to distinguish between the real code and the modified ones?
Whether humans can see the difference?
Yeah, so my use case would be like for attribution of malware. Suppose that I'm a country and I want to appear that another country made the malware. I wonder if even expert human would not be able to tell the difference between modified code and the original one.
That's a great question, thank you. I'm sorry it took me a while to understand it. It was kind of hard to hear. I didn't have time to talk about it in this talk, but we ran a separate study where we actually asked humans to be analysts, basically. We gave them these forgeries and asked them to say, before we told them that they were forgeries, we said, is this code by X or Y? And they did not do very well on the forgeries. But I think if someone is aware of the forgeries, we saw this by the analysts, that they did pretty well at finding the forgeries. So I do think it's possible for a human analyst to tell forgeries, especially if you give them specific training, if they have more information about the authors. So I do think so.
Thank you very much.
Thank you.
Okay. So that was a great talk, and it was a great paper.
Thanks.
I was wondering if you could, if you think there's something in your findings that then people could use to build a classifier that's specifically to look for forgery. Maybe not even that maybe it does worse in the general case, but it specifically targets forgeries.
That's a really interesting question. I think there are several things that you could look for. I think you could look for, so we saw a lot of local modifications. So kind of, if you look for code where like maybe the very local style, the variable names appear like one author, but then you can develop like a higher level understanding of the programming decisions, like maybe where they're declaring the variables, where they're using their variables, how they're treating the data. Like if those don't consistently look like the same author, I think that would indicate a forgery. Thanks.
So do you think if you were not trying to forge other people, like to change other people's code, but that you were trying to change your code, which is probably a much more realistic thing that people do in the wild, do you think it would be easier or harder? And like what, this conclusion?
That's a great question. I don't know. I think it would be easier because you know what the code's doing. And I think it might be harder because you might have a harder time thinking about other ways to solve the problem. Like how do you solve a problem in a way differently than you normally solve the problem? I think that would be difficult.
Yeah. Thanks for the talk.
Thank you.
In light of the sort of, you did this nice analysis about the types of changes people made locally and so on. Did you look at, in the classifier, like how that affected the different features in light of what sort of Edwin's question? It seems like just looking at this that it would, that you'd see much heavier changes to the layout and lexical features, whereas the abstract syntax trees, except for the cases where people were making the more algorithmic changes, but maybe not all of those, you'd see this interesting disparity. Did you do any feature analysis like that?
We did, yeah. I didn't have time to talk about it. I'm sorry.
It's cool. I know you did a lot.
Actually, I was expecting that as well. I was expecting to see that people were mainly changing the lower level features, and we actually didn't. We saw that there were a variety of features changed. We did an analysis of comparing original and forgeries, and I believe there were like 2 features that were constant. And there was no good reason that they were constant in all files. It was just that they hadn't been forged by those particular forgers. So I don't think there are unforgeable features. And yes, the answer is yes, that people changed a variety of features, even though, yeah, sorry.
Interesting. Thank you.
So the same kind of stuff has been done in natural language, right? Where essentially if you try to change your writing style or try to change someone else's writing style or imitate someone else, you can trick the classifier. But I think some of Rachel's work has shown there that then the confidence levels of the classifier aren't as high, so these samples are actually pretty easy to detect. Did you note this when you were looking at your results?
We did not, but I think that'd be really interesting to look at and could be another way of detecting when something's a forgery. That's an excellent idea.
Last question.
Okay, I have an ethical question. So it seems that what we're doing here is proposing a system that uses the code of many, many developers that are in open source and free software or whatever projects to surveil on them and their colleagues. And I'm wondering, have you thought about when is this acceptable and not acceptable, and what are the chances, for example, that employers would start taking this to check on the productivity of their coders, which they already do, and I've also heard that governments will use these kind of techniques to conceal the fact that they're actually doing much more intrusive surveillance. Mm-hmm. So they'll say we found attribution using these methods when in reality they've been doing much more intrusive surveillance of coders. So I'm wondering if you have confronted these ethical questions and what you think about them.
Personally, I have opinions about these. I think these have been used in practice. I'm not an expert on ethics. There is an example of an Iranian developer who was sentenced to death for writing photo sharing software, which was used for explicit material. So that's an example of where you might want to evade it, and I personally think that would be ethical, but I think it really depends on the context. Maybe you're a company and you want to be sure that the people you are paying are actually doing the work. I think there's a variety of situations, and you really have to look at the specific situation. And it really depends on who it is.
Okay. Thank you very much.